Here we're going to look at a technique of integration or anti-differentiation called anti-differentiation by parts, which will help you if you're looking at an integral that has the product of two functions in it, one of whom you can interpret as a derivative and the other one as an antiderivative. But in any case, it undoes the product rule, so that's why we're going to start here with the product rule. So the product rule is a differentiation rule. It's written here. So in order to derive integration by parts, what I'm going to do is take the antiderivative of all the terms. Now when you take an antiderivative, technically we should sneak in this dx so that we indicate what variable we're taking the antiderivative with respect to. So the left-hand side just becomes the antiderivative of the derivative of uv with respect to x, which just becomes uv. And on the right-hand side, the antiderivative of u times dv dx with respect to x is just u times dv, that integral. And then on the second term becomes the antiderivative of v times du. So far, doesn't look like this is at all interesting. I mean, a powerful formula should have no integrals in it anymore. But what this will do, if we isolate the u dv part, if I isolate this part, then what I get is integration by parts. So I'm going to keep that on one side. So the integral of u dv equals, so I kind of swapping places with the uv and that guy. So that is going to be uv minus the integral of v du. So I kind of snuck that algebra in there, but if you solve for u dv, you should get that integral is equal to uv minus the integral of v du. So this is integration by parts. Now it doesn't look like it's that helpful because it's supposed to be this formula, but when I apply it, if I look at the left-hand side, let's say that's the integral I was dealing with. If I apply it, it actually gives me another integral over here on the right. And that doesn't seem like it's that helpful, but when you apply integration by parts, what you hope is that this new integral that shows up, you hope that this is easier, so hopefully easier to integrate. Than the original. Alright, so if you look on the left-hand side, inside that integral, you have the product of two functions, right? You have u times a dv. So what you're sort of doing when you do these problems is you're viewing one of the pieces as a function, in this case u, and another piece as the derivative of a function, in this case dv. So let's see how this works on a problem here. Let's try to evaluate the integral of x e to the x. At this point, the first thing you might want to try is, what you should acknowledge is that substitution wouldn't work. Substitution would work if this was x e to the x squared. Then it would work because you could let u be x squared. But these two terms don't differ by a degree. So we can't do that. So what I'm going to do is I'm going to use integration by parts, and I'm going to assign one of these pieces to be u, and another piece to be the dv. So a rule of thumb is you'll want your u to be something whose derivative gets simpler, and you'll want your dv to be something whose antiderivative is easier to take. So I'm going to let my u be x, and I'm going to let my dv be e to the x dx. And now what I do is I take the derivative, so I want to say differentiate, and I'm going to take the antiderivative of this piece. So the derivative of u, so we take the derivative of both sides, we get that du equals dx. We'll use the differential notation there. And then the antiderivative of dv is just v. The antiderivative of e to the x dx is just e to the x. And now I apply the formula. So this was u, and that was dv. So according to my formula up there, that's equal to uv. So this is this whole integral. So x e to the x dx is equal to uv. So that's x times e to the x minus the integral of v du, it says up here. So that's v, which is e to the x, and du is just dx. And so what we were hoping to have happen actually did happen. Notice, yes, my formula gave me a new integral to solve, but the antiderivative of e to the x is easy. Right? So this is going to be x e to the x minus the antiderivative of e to the x, which we know is just e to the x, plus c. So that's really what you hope for when you're using integration by parts or anti-differentiation by parts. You're just hoping that if you make the right choice, that it spits out another integral that's easier to handle. So as a rule of thumb, I'm going to just give you a rule of thumb for what you should let be u. I'm going to do more examples in the future, but as a rule of thumb, I'm going to put up here, or down here maybe. Just a little note. So you want your u to be something whose derivative becomes simpler. So like polynomials are a classic example, right? They become simpler when you take their derivatives. And dv to be something whose antiderivative is manageable, meaning easy, somewhat easy to find, or not too much of a headache to find. You don't want to make your second integral as hard as the first one, because then you didn't make any progress. And there's a little hierarchy that you can refer to, at least in the beginning, that might help you. So what to let be u, I'll put that up here. In general, this little acronym, LIPIT, can be useful at the beginning. What do you let u be? Well, if you see a log, you should definitely let your u be the log first, because the antiderivative of a log is hard to find, so you wouldn't want it to be dv. So if you're going to use this technique and you see a log, you should let u be the log. The next thing on the hierarchy would be inverse trig functions. The next one would be polynomials. Then exponentials. And then lastly, trig functions. You can see why exponentials and trig functions are at the bottom of this hierarchy, because letting them be u, well, your derivative would not get any simpler. Exponentials and trig functions generally have a sort of a cyclic behavior with their derivatives. So, but log, inverse trig functions, and polynomials all generally get simpler when you take the derivatives. So that's why you'd want those to be on the top of your list for your choice of what to let u be. So we'll do more examples in future videos, but here's a good introduction to integration by parts.